Okay, good morning, everybody. Having a great time? Good morning. Okay, I think this AIAA Propulsion and Energy Forum is off to a great start. Wasn't that a wonderful day yesterday here? Let me know. Was it a good time? Okay, a great start. Welcome to day 2 of the AIAA Propulsion and Energy Forum. I think we've had a great start, and we have an even better day for you today. As a reminder, if you're watching on live stream, or if you're in the audience, please use the Conferences I/O system to ask questions to our speakers. Instructions are on the inside cover of your program or on the screens here in the ballroom. I would like to take this opportunity to thank our wonderful sponsors of this forum for their support. Without the generosity of the companies on the backdrop behind me, we could not present this forum. Please join me in thanking our sponsors. At the end of this session this morning, we have some important announcements to make about the rest of the day, so please stay for those announcements. The theme of this forum is Innovations in Propulsion and Energy, Driving System Solutions. So we've got a great plenary panel set up for you this morning entitled Game-Changing Developments in Propulsion and Energy. And it is my pleasure to introduce the moderator of this panel, Dr. Janet Kavandi. Dr. Kavandi is the Center Director at NASA's premier Propulsion and Power Research Center, the NASA Glenn Research Center. So please join me in welcoming Dr. Kavandi.
Wow, it's going to be hard to match that level of enthusiasm, but I will do my best here this morning. Thank you, Mike, for arranging this session and for inviting me to be here. So we have a very distinguished panel this morning, and I'd like to start by introducing the gentleman here on stage. I will start with Dr. Tom Markusic. Tom is the co-founder and chief executive officer of Firefly Space Systems. Prior to co-founding Firefly, Tom served in a variety of technical and leadership roles in new space companies. He was vice president of propulsion at Virgin Galactic, senior systems engineer at Blue Origin, and the director of the Texas test site and principal propulsion engineer at SpaceX. Prior to his new space work, Tom was a civil servant at NASA and with the U.S. Air Force, where he worked as a research scientist and propulsion engineer. He holds a PhD in mechanical and aerospace engineering from Princeton University. Next, we have Dr. Jay Littles. Jay is currently the Director of Advanced Launch Programs for Aerojet Rocketdyne, based in Huntsville, Alabama. In this role, he leads a cross-site team that develops next-generation propulsion systems and technologies. The work conducted by his group ranges from conceptual vehicle studies and analyses to analytical tool development, materials and manufacturing technology development, booster, upper stage, and in-space propulsion system development and demonstration, and the development of advanced systems. Previous to his current position, Jay held roles as manager of the Structures Integration and Advanced Component Life Prediction Groups and Structural Alloy Development Groups at Pratt & Whitney, as well as serving as an assistant professor in engineering mechanics at the University of Virginia. Jay received a bachelor's degree in mechanical engineering and a master's and PhD in engineering science and mechanics, all from the Georgia Institute of Technology. Next, we have Dr. James Maughan. James is the Global Technology Director at GE Global Research. He supports all of GE's industrial businesses by leading a global team of researchers in developing breakthrough technology in the areas of combustion, aerodynamics, fluid mechanics, heat transfer, and mechanical systems. Previously, James served as General Manager of Product and Warranty Service for GE Wind Energy, General Manager of Controls and Power Electronics, and Global Manager of Energy-Related Research. Earlier in his career, he worked aircraft engine combustion and gas appliances. He led the introduction of low-emissions combustion systems into GE gas furnaces at GE Energy and held leadership positions in gas turbine steam turbine, and energy services. James received a bachelor's degree from Brigham Young University and a master's degree and PhD from Purdue University, all in mechanical engineering. Gentlemen, thank you very much for joining us today. It's truly a pleasure to have you here, and I thank you for your time for being with us. And before I go into our panel members, as Mike mentioned, I'm the relatively new director of the Glenn Research Center in Cleveland, Ohio. For those of you who are familiar with NASA, you are probably aware there are 10 NASA centers, 4 of which are research institutions, and Glenn is one of those 4 research institutions. We have 2 campuses, one at the Cleveland International Airport, and that's called our Lewis Field Center. At that facility, we have several wind tunnels ranging from subsonic through transonic up into the hypersonic regimes. We have a lot of customers who are probably here today, and we work with everything from commercial component type research all the way through defense type research. We also have a second facility in Sandusky, Ohio, which is about 50 miles west. This is our where we have our space power systems test facility. It's got some of the most, if people have been there, they will remember it. It's the largest thermal vacuum chamber in the world. Is a 100-foot diameter vacuum chamber. We have the most powerful acoustics and vibration chambers in the world there as well. So there's a lot of work going on with Orion out there right now. It's actually on the vibration table as we speak, getting tested there. So a lot of work going on with respect to propulsion. We're about half aeronautics and about half in the space. With respect to aeronautics, again, we do everything from component level work all the way through entire engine tests. We can test in vacuum. We can test space, full engines in the B2 chamber out of Plumbrook, and we are designated as the NASA's premier center for electric propulsion. So all the electric propulsion for the agency is focused at the Glenn Research Center. So with that brief introduction, I'd like to now go to our panelists, and I'll invite Tom up to the podium, and he can provide his remarks.
Thank you, Jenna. Okay, where are we mic'd here? Okay, good. Good morning. It's a little early for rocket science, especially for me, so I plan to divide my comments roughly up into 3/4 complaints, and maybe I'll have some ideas by the time we're done. But seriously, looking at the subject, game-changing technologies in propulsion, today I don't think we're really short of good ideas to have game-changing effects. What I think we're short on is game-changing execution. There are a plethora of good ideas in propulsion and aerospace technology that for just one reason or another, they haven't been implemented. We could do a lot of things if we would just implement the technology that our forefathers came up with. I know at Glenn and at other places, we've talked about nuclear thermal propulsion for a long time, and the technology's there. If we want to go to Mars, we could, give Stan Borowski $1 billion, and Stan's still there, isn't he? I don't know, hopefully. Give him $1 billion, and we'd be off to Mars. In the private sector, which I represent at Firefly, I think market forces and competition is actually going to drive the introduction and adoption of these old good ideas. So this morning, I think we have about 5-10 minutes here for each of us to talk, and what I was going to do is highlight one of these old ideas that we're actually going to bring into reality and implement at my company, Firefly Space Systems. So just very quickly, for those of you that aren't familiar with Firefly, we're a startup company, 2 years old. Our goal is to dramatically lower the cost and barriers of entry for launching small satellites, roughly 1,000-pound satellites. Our first vehicle, flagship vehicle, predictably is called Alpha, And Alpha is designed to be a simplest, soonest, very low-cost launch vehicle. And in the course of trying to design a very simple, low-cost launch vehicle, it necessitates going back and grabbing some of this technology, which I think in some ways will be game-changing. So in particular, what I'm going to talk about this morning is the implementation of the Aerospike engine on our Alpha vehicle. So let's see here. Click. Next slide. All right, so people have been talking about Aerospike engines for a long time, a half century, literally. Rao and company worked on these things back at Rocketdyne in the 60s, and it was realized by these early pioneers that there was some very interesting characteristics of the Aerospike concept. Basically, what the Aerospike allows you to do is have a variable area ratio nozzle without any moving parts. All nozzles, conventional bell nozzles, have a variable thrust coefficient relating to the change in altitude, but the gas dynamics in a Aerospike are unique in that it actually evolves into increasingly high area ratios as you ascend in altitude. So you'll hear the oft-quoted phrase that it's an altitude compensating nozzle. Now, despite extensive analysis that shows that these devices can have very high thrust-to-weight ratio, very high thrust density or thrust to cross-sectional area, and average thrust coefficient over the flight profile, no one has actually deployed them on a flight vehicle. So a natural question is why? One answer is maybe it's just a bad idea. One of my mentors, Pete Turchi, used to needle us and say, there are no good ideas, they're just old, there are no new good ideas, they're just old bad ideas packaged up in new proposals. So hopefully that's not the case here, because we're going to go out and fly this and we'll actually find out. So what's shown here are some images of actual ground tests of Aerospikes in different configurations, linear Aerospikes, like they're shown on the bottom center picture there. On the top is a more annular geometry Aerospike. And there's another variation of this called a plug cluster Aerospike, which is kind of like an annular Aerospike, where you divide the annulus into a discrete number of combustors. And that's the approach we're taking at Firefly. So to try to answer the question why, I think I can give that some explanation here in looking at the Alpha vehicle. So in Alpha, we wanted to create something incredibly simple. We wanted to eliminate moving parts, and so that kind of initially just made us want to dispense of the turbo machinery, which are very expensive, take years to develop, have moving parts and failure modes. So how do you get the propellant into the engine? You have to push it into the engine, so you go to something called a pressure-fed configuration. Now, the problem with a pressure-fed rocket is that the propellant tankage and the pressure in tanks and the pressure in itself are very heavy. So the design challenge becomes trying to minimize those parasitic masses, which drives you to want to create a pressure-fed rocket that has as low propellant tank pressure as possible, which consequently means you have low combustion chamber pressure. And the downside of that is that you can't put much of a nozzle on it, because you can only expand so far for a ground launch vehicle before you start to have problems with the nozzle, for example, separating. So it turns out for the pressure-fed rocket, the Aerospike is a very natural solution. It allows us to get additional effective nozzle area without having to put longer nozzles on or increase the pressure, chamber pressure, and hence the pressure of the propellant tanks. So there's kind of a natural synergy there. Another problem with Aerospikes themselves is they're notoriously difficult to cool. They have very serious thermal heat flux issues. However, in the pressure-fed rocket, we have a problem. We need copious amounts of heat to heat this pressurant gas that's pressurizing the tanks. So we have a problem. We have two problems that have combined solve one another's problems. So in alpha, we actually cool the aerospike with a pressurant gas, pulling off a couple megawatts of thermal power, keeping the aerospike happy. And so the message is, overall, from a systems point of view, the aerospike works for alpha. So that's perhaps why this is the first time someone's flying this type of configuration, because there's kind of a natural systems synergy with our pressure-fed vehicle and what the aerospike can do. Okay, I'll quickly go through what the technology looks like. We have a pretty short time for our comments here, so I'll flip through these quickly. I'd be glad to talk to anyone afterwards, but I just wanted to show you the simplicity of our design. So on the right is a breakdown of our thrust chamber, very few parts, a combustion chamber, a pintle injector, which is a great injector for a startup company, is another one of my mentors, Bob Sackheim, used to say you can flush the toilet with this pintle injector and it'll just keep on running. I can tell you at Firefly we've run that injector down to 4% delta P across the injector, and it was chugging along. It wasn't chugging along, it was just starting to chug along, which 4%, for people that work on engines would say that's pretty crazy. But again, for the pressure-fed rocket, if I can get away with low delta P on my injector, less pressure in the propellant tanks, better overall payload performance. So we array 12 of these combustors around an aerospike ramp, as shown in this illustration. The engine overall has about 125,000 pounds of thrust. Typical LOX RP, ISP, and other performance characteristics. One of the cool things that we've been able to do in our aerospike development program is run extensive amounts of CFD. We have a strategic partnership with the University of Texas. We use their 15 petaflop computer Stampede to run probably some of the most advanced computational fluid dynamics that's ever been done on aerospikes. And that's allowed us to learn some things about how long you make the aerospike optimally, and even the surface geometry of the aerospike. We've been able to eke out a few more seconds of ISP in these CFD studies by using more of a fluted geometry of the aerospike versus just a continuous smooth aerospike surface. So beyond the CFD and the analytical studies, we've actually started building these combustors and testing these combustors. So what's shown on the left is our horizontal test stand at our Briggs, Texas facility. Also shown on there are two of the combustors, a research type combustor on the bottom, and actual flight weight combustor on the top. And if you can see, there are like 12 pads around that ring in that front of that test stand, and eventually that'll have 12 combustors and a spike in the middle, and we'll be doing our first aerospike development tests later this fall. We have in-house capability to do A to Z everything. You can see on the bottom CNC machines. We fabricate all of our own chambers in-house and test everything in-house. Okay, so that concludes my presentation here on aerospikes. Thank you for your attention, and I'll turn the floor over.
Okay, thank you. Next we have Jay. Would you like to stay seated, or do you want to stand?
Oh, it doesn't matter. Those
Okay.
Those are not me, though. There. All right, thank you. So I started thinking about, just in the general sense of what are game-changing technologies in the general propulsion and energy area, and how you can encompass that from my perspective, where I currently work within launch and space propulsion. If you look at the picture, just considering where we are, that we are on this planet and we're trying to get out of this planet, which is tremendously difficult, and then to go beyond, to actually try to become an interplanetary species, is effectively game-changing in its own right. the very concept of what we're talking about doing from an exploration perspective is game-changing. So what I thought I would do was just, there are a tremendous number of technologies and developments that are really changing the way that we're doing business now and are going to enable what our near future will be. I'm just going to hit on a few of those, some that I think will really make tremendous impacts, primarily from an exploration type standpoint, but some of them are a little bit are more cross-cutting as well. So if you go to the next chart, kind of a few general areas. Oh, I have the clicker, sorry. The big green button. Sort of the general area of advanced materials and processes has, over the past decades, really done tremendous things for us in terms of, and this is across propulsion, not only rocket propulsion and space propulsion, but also gas turbine propulsion. We have historically focused very, very hard on improving performance, increasing capability, so higher temperatures, higher pressures, higher speeds, improved efficiencies. Recent focus that throughout the industry is really on affordability. A significant focus is on affordability. One of the key areas that you see a little collage here of is the general area of additive manufacturing, just as an example towards affordability. There's another panel that will be specifically on this tomorrow, I believe. Sorry, I'm getting feedback somewhere. But additive manufacturing, when done correctly, and that's the key, when done correctly, it's not a panacea for all things affordable, but when done intelligently and used to take out touch labor to enable new designs, and when done so in a way that we really understand the full capability of the materials and the processes and components that we're producing, really does have tremendous potential in terms of reducing costs by an order of magnitude, lead time significantly, and even in the bottom right is a quickie picture from Made in Space, where actual components are being made, tools are being made on the space station that a drawing is sent up and it's made there, and from a logistics standpoint in the future, how we do operations will have tremendous potential benefits. Okay. The next general area that offers tremendous benefits from an exploration standpoint is the area of electric propulsion. Electric propulsion is a nice example because there are both applications and tremendous significant potential benefits for Earth orbiting satellites. So when we use a EP bus, we can potentially reduce the size of some of these satellites by 50, 60%, which greatly reduces the launch cost. We can make something, we can put multiple satellites in a single launch where historically it would have taken up the entire payload, and or it reduces the cost of the satellites. So there's a significant potential impact there. Additionally, electric propulsion for exploration missions it's very similar, right? We have to carry significantly less fuel because of the much higher efficiency of electric propulsion systems. Consequently, we have to put less up there, so it'll take fewer launches to get our payloads and systems that we want to take well beyond Earth orbit. Okay. So EP has significant potential benefits for where we're trying to go for exploration. And Tom mentioned nuclear thermal propulsion. We've talked about nuclear for years. There have been regulatory challenges and concerns, and there are approaches now that are allowing us to potentially get past some of those approaches by using low enriched uranium, and by doing that with a happy marriage of advanced electric propulsion and then nuclear thermal propulsion, we'll be able to have use EP. We can get pre-positioned hardware for future missions, and then we can use NTP for the manned portion of the missions with higher thrust. So NTP is offering a significant potential benefit for us as well. Now you go beyond just strict technology, but worthy of conversation when we're talking about significant developments and what's changing the way we do propulsion. Significant changes in the way we're doing propulsion development is the entire conversation around commercial space. We could have a semantics discussion on what commercial space really means, but it is everything from commercial entities entirely paying for that propulsion development. And consider that for a minute. From a launch perspective, how many launches do you have a year? If you're only making a propulsion system, the investment for a large propulsion system is relatively high. And so you have to make a business case such that you will get that investment back. Public-private partnerships, another aspect, is where the government and industry are working together to, again, have to justify that investment to do the propulsion development, which is different than what we've done in the past, where a mission has been identified that, like a Mars mission, does not have necessarily a near-term financial ROI, but we know that its exploration is what we want to do. So the whole conversation around commercial is really changing the way we consider how we invest, and it changes how we work with the government from a private standpoint. The insight that the government gets in these types of development programs versus traditional government-paid programs. So there's a lot of changes that are happening with our industry right now based on the commercial activities as well. Okay? Thank you.
Next we have James.
Good morning, everyone. It's a pleasure for me to be with you here in Salt Lake. I haven't spent a lot of time in Salt Lake, but it happens that my ancestry was part of this pioneer trek that was celebrated here in the state with a holiday yesterday. I remember that one of my ancestors wrote in her journal upon arriving here that she had traveled 1,600 miles to get here, had walked most of the way, but she would rather go 1,000 miles further than stay 1 second in this God-forsaken valley. But she did stay, and she plowed and planted potatoes that very afternoon. Anyway, the perspective that I hope to bring to this panel is more on the commercial, practical side around propulsion, around energy, and share some examples from GE that maybe not game-changing, but certainly have made progression over the years that I hope will be interesting to you and helpful to us as a panel. First, I'd like to start with not quite going here. There we go. Okay, first I'll start with the example of our GE LEAP engine, which is the only engine certified for the 737 MAX, also certified for the A320neo, along with Pratt's geared turbofan engine. And just enormous technology advances have gone into this engine. And there's too many to cover right now, but I certainly would like to mention the 3D printed fuel nozzles which are in the engine. And what's particularly gratifying here is this is not just an example of where we're eliminating the complex manufacturing and the brazing processes, but beyond that, the engineers have actually thought, now that we're doing this, what capabilities can we add to the fuel nozzle that we could not add in any other way, which is very gratifying to see and I think very important. Of course, enormous advances in materials technology, tie aluminide, CMCs on the first stage shrouds, clear advances in that type of technology. And now after the recent air show, we have 11,100 orders for this engine, which to me feels like a big swing because the first one has just been delivered for commercial service in the last couple of weeks. And still enormous advances, and this is going to be significantly better than the CFM56 that it replaces. Another example of technology advances here would be on the GE9X engine, which immediately is on the heels of the LEAP engine. And the same kinds of advances here around aerodynamics, combustion, heat transfer materials, but now taking that to the next level. This is an enormous engine with a 134-inch diameter fan, the whole thing bigger really than a 737 fuselage. Pushing the pressure ratio now for a simple cycle application to 60 to 1, which is essentially approaching the Saturn V rocket conditions. It's very impressive. 1,400 degree compressor exit temperature, which is higher than the turbine inlet temperatures used to be on our first turbo machinery products. Again, CMC's here pushing now not only from the hot gas path shrouds, but into the combustor section, further into the hot gas path where there are enormous advantages. Again, relative to the GE90 for the 777X, which is the aircraft for this, where I think we have roughly 1,000 sold, maybe 800 to 1,000 of these on order as well. These advances in aviation directly port over into our power business. Of course, GE has both of those businesses, both roughly $25 billion businesses, and our flagship on the power side is now this 9HA gas turbine, which has a very impressive 62% combined cycle efficiency. The same types of technologies that are in the aviation are used in our power business, but they're tailored for this particular application. So it's not how do you maximize performance over a 2-minute takeoff and then cruise after that. It's how do you optimize performance for 3 years of continuous operation. And so the technologies have to be tuned to that. A combined cycle application, which means that the pressure ratio is not as high because you need to conserve some energy in the exhaust for the waste heat recovery and the boiler that follows it. Our two businesses have a lot of friendly competition here, arguing over who has got the more complicated design cycle. Certainly each of them thinks that it's more complicated in the business that they're in to design something for 2 minutes or design something for 3 years of operation under the various conditions and constraints, but a lot of interaction between those two. And I mention that because power and propulsion not only have common customer and technology demands, but this is a common across many industries. The kinds of things that are being driven from a society's perspective about noise and emissions and regulations and fuel choice and long-term environmental impact, these things have to be balanced against customer concerns about what capabilities do they need, how do they make money, how do they turn a profit on these things in order for long-term sustainability. And the technologies that have gotten us this far around materials and aerodynamics and combustion, the kinds of things that we've talked about, have certainly been very effective, and they're the technologies that are going to be required carrying us forward as well. And by that I don't mean to be dismissive of any game-changing technologies that might come on, but I wouldn't want to leave the perception that only game-changing technologies can give us advances. We'll talk more about that later, but it's very important. Nevertheless, let me highlight a few things, again, that would be helpful across all of our businesses. One certainly would be the ceramic matrix composites. You're familiar with these, with the silicon carbide matrix that is in there, the fibers that give this material such enormous strength and ductility, at least for a ceramic, and the kinds of applications that we have across our power aviation industry and also other applications that are in development. But the point here is that not only is it a great material, but we need to learn how to design with this material. And that's been a big breakthrough, I would say, for us, is learning how to use these materials. The design rules are all completely different. The methodologies are all completely different. These are not metals. We've had to develop a lot of technology to do that. But it's been very effective, and GE is all in. There's no turning back. The bridges are burned, as you would say. And the kinds of plants that we're now building to manufacture this material, to manufacture these components, are going to be very important to the future of both our power and our aviation business. Changing a single component to CMC, the stage 2 blade on a power turbine, can deliver an additional 5 megawatts by itself by reducing the need for cooling air. So it's very impressive technology. A second one I'll highlight is about digital plus physical, really like never before. This is a theme that's been with us for a long time, but is now really exploding. And I'll just highlight the one thing there, which we call the digital twin, which is about personalized engineering models, the ability to do something very specific for a particular engine. So not to say that this engine has had 1,000 flights, 1,000 cycles, so its oxidation, its creep must be so-and-so, but rather to take every single flight. It went from this city to this city. These were the conditions at which it took off. This is the air through which it flew. This is the dust that was there on that day. This is where the pilot accelerated. This is the cruise, all those conditions, and calculate for each individual component in the engine, what were the temperatures, what's accumulated damage for creep, oxidation, low cycle fatigue, et cetera, and to put that together in a way that's far more detailed than we've been able to do before, and it's all about computational power. So very impressive advantages occurring there. And then lastly, I'll talk about future propulsion systems as a possibility as well. The curve on the bottom depicts that the Brayton cycle turbofan has been around for a long time, more than 50 years. All of us flew here in aluminum tubes with a turbofan or two under each wing. Will that change in the next 50 years? I don't know. I wouldn't want to bet against the engineers who are working on those products today. But clearly there are other technologies out there that could be huge for us in the industry. Other propulsion technologies about open rotor and the kinds of things that I'm sure you're familiar with and that we'll be talking about. These things could be a leap onto a new technology growth curve. Of course, there are huge technology gaps that need to be bridged in order to make that happen, one of which is electrification and electrical technologies, which could help significantly in getting there, as well as, of course, all the core technologies that we have. So I'll just leave with the final thought that none of us can see the future, none of us knows for sure what's going to happen, but from where I sit at GE, at the Research Center, the technologies that we look at, I think the future for us and for our industry, both on the power side and on the propulsion side, is very bright. And so with that, I'll thank you for your attention.
Thank you very much, James. Thanks to all of our presenters today. So we have several questions from the audience that are filling in, and please continue to add your questions. I will go right now to the highest rated one, which is probably directed to a couple of our panelists. How has the billionaire class investors-backed companies changed the game of space launch, and how has it affected traditional providers such as Aerojet, Rocketdyne? So let's start with Tom, and then we'll ask Jay to follow up.
Okay. So the question is, how has the involvement of billionaires investing in commercial space changed things?
Yeah, how's the billionaire class investor-backed companies changed the game space?
I personally worked for 3 of them, and I ran out of billionaires, so that's why Firefly started in the first place. No, we owe a huge debt of gratitude to those folks, and companies like Firefly absolutely could not exist if they hadn't been kind of the pathfinders and flag bearers for this new space movement. The reason being that this is a very capital-intensive business. So I have to walk in as I'm not a billionaire, not even a millionaire. So I have to walk into these venture capital firms and say, hey, how about you give me $100 million and we'll go do something cool. And that would have been impossible to actually get a positive response if Elon and others hadn't gone before and shown that it's actually possible to create a highly profitable business doing this sort of thing. So they really planted the seeds for new space and opened up the opportunity for many other companies to come in the wake of that, including companies like Firefly and others.
Thank you, Tom. Jay, would you like to answer for Aerojet?
Sure. So I'm notably the type of company that's been in business longer. We don't like to say old space. And so I think my answer will surprise you. We actually are very excited the way things have transpired, especially from the perspective of, these companies have really started a conversation, right? And the attention that new space has gotten has helped us all across the board. So getting people excited about space, getting excited about launch, about the potential to take people to Mars is fantastic for us. It's good for all of us. It's good for all of the industry. Where we have challenges, there's the good, the bad, but the area that I mentioned previously, just briefly, but with the vastly different types of contracts that legacy versus some of the commercial contracts, they're different in the amount of insight that the government regulatory agencies get, and that could introduce challenges down the road. So as we move forward and we learn more about how we all do commercial space, getting that delicate balance of the right amount of insight without too much process and too much involvement, I think is going to be good for us all.
Okay, thank you very much. Most of our questions are trending toward the space side, but I did want to ask James. I know GE is working also towards hybrid electric. What do you see as one of the greatest challenges if we were to go to a hybrid electric system for commercial aircraft?
So on hybrid electric, GE is looking at a lot of technologies about that. And the thing that's probably most captivating at this point is the system impact of it. And by that I mean not only the electrification system, but also the aerodynamics system. Putting a propulsor, what's most intriguing to me is a propulsor at the tail of the aircraft where you can capture the low momentum boundary layer and accelerate that and get the system propulsion advantages of that. But what's interesting on that is the trade-offs that you make in doing that and how you would have to redesign a turbofan engine to compensate for that. Because you can easily give back through unsteady considerations, through non-uniformity considerations. You can easily give back the bulk of what you think you're capturing there, depending on what assumptions you make. And so we're very enthusiastic about those kinds of possibilities, and of course all the superconducting equipment that would require to get the power densities that are required for that as well. But what's most intriguing, I think, to us at this point is how do you integrate a total system to get those kinds of benefits in a practical application?
And I know that we're talking propulsion here, but we also are talking energy, and energy storage is a big challenge as well, trying to get the high energy density storage capability that's safe to fly on aircraft.
Yeah, and you know, when you mentioned the billionaire thing a minute ago, I thought, well, my first thought was $1 billion will get you about halfway to a new aircraft engine. But the things that these billionaires are doing, like Elon Musk and others, you know, it may or may not turn into reality, but it drives energy into the system. By that I mean innovation. Certainly the things that he's doing with storage, Tesla, automobiles. Imagine the impact on the total system if every garage had an electric car that could store power from renewable energy during the day, use it at night, shift from, you know, those kinds of things could really transform the industry. And that kind of private investment can drive things in that direction in a fast way.
Okay, very good. Thank you very much. So the next highest trending question is LOX methane really the game changer that it's touted to be? So let's see, how about Tom? Do you want to talk about that?
Okay, so as I mentioned earlier, Firefly is using LOX RP propellants in our first vehicle. I'd started off thinking we would use LOX methane, but at the end of the day, it didn't fit the simplest, soonest approach, and it wasn't synergistic with our design, which again demands low pressure, and methane ends up having problems at lower pressures when you're looking at regeneratively cooled engines. Having said that, yesterday I was on a panel where we were talking about reusability, and I think when we start getting into reusability, methane is going to be very supportive of that, in that propulsion systems that operate on methane are cleaner burning, are much more serviceable. For example, when you come back with your reusable vehicle and you have a propellant that has, you know, very high vapor pressure, it's gone when you get back, which is nice, versus like a RP, which you have to go and do a cleaning operation every time you run the engine. So I think it's going to be an important part of the reusability equation. As far as the broader uses of it in propulsion, I'm not so sure. I haven't had enough time to think about going to Mars and things like that, but it seems like the folks that are definitely looking at it very carefully.
Thank you. Did you want to add anything, Jay?
Yeah, so you know, there has been a lot of interesting conversation on LOX methane, and from if I put on my technology guy hat, it's cool. I think that if you look from a launch perspective, we have so much history and knowledge and experience, some of it hard fought, right, to really understand both hydrogen and RP, both of which, depending on your preference, you know, we serve us very well, especially from a launch perspective. So investing in methane from a launch perspective, I really don't understand. Tom mentions reusability, which is a good point, and that's commonly, you know, brought up as a rationale for LOX methane for reusability. However, you know, if you've ever probably not a lot of you, but I'm sure a few of you have looked at an RD-180 after it's been run. So a ox-rich staged combustion engine is a very, very, very clean running LOX RP that is tremendously amenable to being reusable. So that's an RP that's tremendously, and we, you know, it's a proven cycle. We're making one domestically in the United States now. So there's, I really don't see from a launch perspective a need for LOX methane. Where it does become very interesting is for some of the, if you're, you know, I mentioned EP and NTP for the in-space missions. Well, if you're doing chemical propulsion for in-space, the nice thing is the oxygen and the methane, relatively close temperatures. So from an in-space perspective, that could be good. From a future on Mars, the ISRU, so being able to capture the fuel locally there would have benefits there. So I think from a summary is launch, I really don't get it. In space does look like there's some good future uses.
Can I make one more comment on that? Another thing that comes to mind is, again, game-changing launch vehicles in the future may use air-breathing, a combination of air-breathing propulsion and conventional rocket propulsion. And in some of these high-speed combustion systems like scramjets, the chemical kinetics might favor using rapidly reacting propellant like methane. So that's another area where I think it could pop up and be supportive of game-changing developments.
And you know, it's not quite the same, but I wonder if we can see a future where LNG aircraft could be a bridge or an entry into some of those types of technologies, certainly on regional type things. And you know, there's an enormous amount of natural gas in this country and others around security and cost. Could be some significant advantages. Big technology hurdles as well, but could be an application.
Okay, thank you very much for that. The next one is specifically for Tom. Why did you pick 12 engines for the plug cluster Aerospike on Firefly Alpha? What's the magic number?
12 pops up all over the place in history, and it just seemed, no. No, one of our principles at Firefly and in making Alpha is that we want to make lots of the same thing, lots of small things instead of you know, one big thing. And it just turns out it's a lot easier to make small combustors and from a tooling perspective, from a propulsion combustion stability perspective. But one of the key things is we wanted to use the same basic combustor on our upper stage and our lower stage. And to accomplish that and get the requisite thrust, if you use one of this standard combustor on the upper stage, turns out you need about 12 of them on the first stage to get the requisite thrust to weight that you need. It also turns out, if you go back and look at the literature on this plug cluster Aerospike configuration, it's about at 12 where the behavior of the plug cluster Aerospike with 12 combustors starts to asymptote and to look more like the continuous annular Aerospike as far as the gas dynamics. So it's kind of a good sweet spot for those two reasons.
Thank you very much. Okay, the next one is something that all the panelists would be welcome to comment to. It says, what skills should be fostered in the upcoming generation to enable them to contribute to the game-changing realms? So James, why don't we start with you?
You know, a couple different ways to answer that question, but a phrase that I've heard recently several times is that we make progress one retirement at a time. And by that I mean people need to be open to new ways of doing things. And you know, by the very nature of our businesses, both the large power equipment, large oil and gas equipment, certainly aircraft engines, people tend to be naturally conservative about that. And all of us that fly or get power, we like that conservatism. But if there's a skill that people need to think, if there's a skill that people need, they have to have the ability to think about the big picture a little bit more openly, maybe in the past, and be willing to try new things and push in different directions with all the right checks and balances. But driving innovation, driving an innovation culture, and getting people that support that is a huge challenge, I think, for the future.
How does GE approach that?
So we try to select people that have that kind of thinking, and we try to drive innovation as well. One of the things that we do at the Research Center and in our businesses as well is encourage people to spend some fraction of their time thinking about other things. For instance, specifically at the Research Center, we have programs that are geared towards 5 to 10 year time frames, things that frankly we know are not going to be successful. That did come out quite right. But things that people can work on that will be highly innovative, that they can think about that, have that drive that creativity, and then that spills into other things that we work on where less creativity is encouraged and more actual results are needed.
I think we do the similar things at NASA. It just comes down to when you have a deadline and you have a project that
Right.
people tend to put innovation kind of on the back burner sometimes and do the practical thing that,
Right.
they have the
And
charge number 4 or whatever.
You maybe even saw in the paper over the weekend, Google is now, even at their research lab, is driving for some actual results as well as some long-term thinking. So hitting that balance.
Jay?
So I can think of kind of 2 general areas that I think are going to be increasingly important. One, I think as much as people can do to try to get a broader range of experience, historically, if there was a very large company and you could grow up in a very large portion within this engineering discipline and people could spend a career moving up a relatively linear progression. It's become much more important, I think, that people be much more broad and try to rotate around. Listen to Tom's resume, right? Where has he not been? You've done so many things in different areas, and getting those experiences, I think, helps you understand not only the various technical aspects, but the business acumen and the overall community. So I think that's really probably one of the key things that we need to do. And to be honest with you, number 2 just left me.
When I look at the generation of engineers coming up, there's 2 conspicuous things that I see that are problems. One is that for whatever reason, students aren't coming in with a really solid grasp of the fundamentals anymore. It just amazes me. I sit down in hundreds of interviews and just go through some basic stuff, and it's like, well, I took the test, I did well, and that's it, and I forgot it. And I don't know why that is, but there seems to be a trend that way, and academics in the audience, something to think about. Right. The second thing is experience in actually building vehicles that can go to space. We have a generation of people that laid the foundation for space exploration and vehicle development, and they're all retiring. And there are very few, the next generation coming in, that actually know how to build these machines practically. And there are only a few companies that you can find people that have practical expertise. So we're having to learn a lot of things from scratch. So the last thing I'd say is I'd encourage all the young engineers that are coming out of school, don't take a job where you're not going to be able to follow a project through space flight hardware and actually flying something. You'll distinguish yourself because you'll find yourself that you'll be a rare commodity out there right now, and something you should pursue.
I think those are all very good points. We're faced with the same kind of issues that you gentlemen are, bringing in new people. We want to make sure we give them hands-on experience and allow them to fail, because sometimes when you fail, that's when you learn your biggest lessons. You don't want to fail, at the wrong time too late. You want to fail early and learn what that's like, and then learn your conservatism where it should be applied, and then learn to be a little risky where you can afford to be risky as well. So thank you very much. Let's see. This could also be, it just skipped. What do you think is the most influential game-changing technology that will enable space access for payloads? So, Jay, why don't you start with that one?
Space access for payloads. So beyond the way we do it now?
The most influential game-changing technology, maybe forward-looking.
Okay, so again, we can launch payloads now. The primary focus that we have these days really is on affordability. There are a number of technologies that let us get there. I briefly mentioned the additive manufacturing. That's huge. It's not the only one, but there are a number of manufacturing processes and activities like that that'll allow us to increase our affordability. But I mean, to be honest with you, I mean, Tom's got an interesting approach here that from the aerospike perspective, you know, that also has an air toward, it's a technology and has an air towards affordability when integrated with the entire vehicle. I think most of the things that we're really going to focus on these days are less in terms of improving, you know, launch propulsion capability in the purest sense, but moving towards providing those capabilities with the same reliability, but doing so much more affordably.
Okay, thanks. So we got a lot of questions here that are specifically for Tom, so I'm trying to spread this around a little bit, but here's the highest trending question. It says, LA seems like such a new space hub. How did Firefly choose Texas for its operations?
That was pretty easy. I've worked for all these companies. I've worked in California. I've worked in Texas. The business climate in Texas is extraordinary, but it's not obvious why Austin, Texas, and the reason is we chose Austin, Texas for spouses. When you're trying to recruit people to go do this kind of stuff, it's super exciting. The engineer is always like, yeah, let's go, and often the spouse is like, have fun, honey, out there in the desert in that godforsaken place working on that stuff. So Austin is a thriving place where the engineer that's coming to work can have a cool experience and the spouse can find cool things to do as well. I could talk about it all day, but that's really one of the principal reasons is for the spouses.
Okay, thanks. This is another one that says for Tom, but I think it would apply to everyone on the panel. How do you balance keeping investors happy while also taking necessary risks for the next generation systems? We touched on that just a little bit earlier. But Tom, since it's addressed to you, want to start, and then I'd like for the other two panelists to comment as well.
I haven't found the need to balance it. The investors invest in people, and if they're investing in you, they believe in you, they believe in your vision, they give you the resources, and they step back and let you do your thing. So I haven't found a conflict in that way.
Similarly, I think we have a significant amount of government customers, and we work with shared visions of missions that we're going to accomplish and satisfy them from a private perspective. You know, we do have to evaluate how to spend our resources based on some assessment of return, because we are a public company. But that said, you know, the work we do is inherently exciting. We demonstrate that there's a profitable business there or a potential for one, and at the same time to do things that excite the younger generations. It's really that's not our hardest part.
Great, and James?
And I would say our investors over the years, I think, understand that both in power, large oil and gas, and certainly in aviation, these are long-term investments that you need to invest now many billions to develop a product. It's not going to be cash flow positive for many years after that, but eventually over a 20 or 30-year cycle, like the GE90 is in now, it has significant return for investors, and that sustains the process to then develop the next engine. So it needs to be sustainable, and if you're not profitable, you're not sustainable.
Okay. Well, we are out of time, and I wanted to thank all of our three panelists here today. It's been a pleasure to moderate this session. That was very informative, and we have a lot of questions that we were not able to get to, but I'm sure people will try to find you afterwards and ask those questions. So, and we want to go back to Mike Heil, but thank you very much for your presentation here today.
Thank you.
Thank you, Janet, and panelists for a very informative discussion. I think you gave us a lot to think about. I'd also like to thank the audience for very thoughtful questions. Coffee is available out in the exposition hall until 9:30, so it's a great networking opportunity for everybody. At 9:30 a.m. in Ballroom F, we'll have our next Forum 360 panel, which will be on liquid rocket propulsion lessons learned. We're going to have a luncheon in the exposition hall this afternoon. If you don't have a luncheon ticket yet, they are available and on sale at registration. And our afternoon plenary panel, High-Powered Systems for Aerospace Applications, will start right here in this room at 1:30 p.m. We hope you join us for that. So please enjoy your morning. How about another round of applause for our panel?